LiDAR technology is undergoing a rapid and fundamental transformation. The field is moving away from legacy scanning-based systems toward compact, solid-state architectures that are low-cost and scalable. This promises to transform LiDAR from a necessary evil into a reliable and inexpensive modality. This transition is driven in large part by the emergence of high-resolution single-photon avalanche diodes, or SPAD, arrays. Dense pixel arrays in future LiDARs will turn these devices into more informative cameras, with data resembling a well-established modality, allowing for a future in which camera and LiDAR processing pipelines merge. Fully flashed LiDAR systems are needed in tasks with highly dynamic environments, such as autonomous navigation, due to the need for low acquisition times. Legacy scanning systems are slow and suffer from motion-related artifacts, which flash LiDAR systems can avoid. However, this change also brings with it new failure modes. Traditional cameras have long struggled with, and adapted to, a phenomenon known as glare. In flash LiDAR systems, this problem once again becomes an issue. A bright return which enters the system causes light that should ideally be focused onto a single pixel to redistribute across a wider neighborhood. This redistribution creates false or phantom structures, while suppressing true returns from real surfaces, resulting in LiDARs seeing what is not there and simultaneously missing what is there. In safety-critical applications like autonomous driving, this can mean a vehicle coming to a complete stop in the middle of a highway, or going through an intersection at the same time a child is trying to cross the road. One of the most common culprits for these bright returns are retroreflectors, which are a common occurrence on the road. These objects are deliberate and ubiquitous components of modern infrastructure. Constructing a realistic scenario without glare sources may indeed be harder than constructing one with them. They are on all traffic signs, road paint, construction equipment, and many recreational objects like bikes or scooters. One might ask themselves, why has this failure mode remained largely invisible to the research community? This is because traditional scanning systems avoided this issue through costly and mechanically complex hardware design choices. We develop a training-free approach that operates on low-level LiDAR detections, or echoes, prior to point cloud formation. A key observation is that in the measurement space, the physics of internal glare can be modeled as a linear, scene-independent operator acting on an ideal, glare-free transient histogram. We refer to this operator as the Transient Glare Spread Function, which we measured in lab to reason about the likelihood of each detection arising from glare. Our approach does not depend on retroreflector size, shape, or distance, and can operate with multiple retroreflectors in the scene. Using experiments with real single-photon LiDAR hardware, we demonstrate substantial suppression of severe glare artifacts while preserving true scene structure. Importantly, this method integrates naturally with standard LiDAR signal processing pipelines and can be deployed on unmodified commercially available sensors.